is Module 10, Lesson 1. It's time to talk about chemical reactions. So what we're going to look at for this is some chemical equations or chemical reactions and the terms that go with it. So I have on the screen some things that you need to know. We'll be using these as we go. Let's see, I might make it move as I... Oh, there we go, there's my mouse. So the first term up here is coefficient. Coefficients are the large numbers that go in front of a chemical formula or an element. They're just like coefficients in math class. In math class, if you have 2a, that means 2 times a. If you had 2ab, that means 2 times a and 2 times b. The same way here, this 2, it means 2 H2s and also 2 O's. The reactants are the things on the left-hand side of the equation, and the products are the thing on the right. The reactants are kind of like the ingredients of what goes in, and the products are what comes out. You read the arrow here as yields. So the way that you would say this entire reaction right here is you would read it as 2H2 plus O2 yields 2H2O. Now, the reason that we want to get really good at this is because the only other way to do it is to write this out in words, and that gets really, really labor-intensive and really long. It's also hard to put the coefficient in front if you don't see the formulas. So make sure that you know these 4 terms, and we'll be good to go. All right, here's a little bit more vocabulary. A skeleton equation is just the reactants and the products written with their proper formulas, but it does not necessarily have to be balanced. The equation on the previous screen as a skeleton equation would be this. It'd be H2 plus O2 yields H2O. Balanced means that you have the same numbers of atoms on both sides of the equation. So for example, right here, there's 2 hydrogens. Well, here there's 2 hydrogens. I mean, that appears to be balanced. Right here is 2 oxygens, and here is just 1 oxygen. So this is not balanced. This is an unbalanced equation. That makes it a skeleton equation. We're going to write the skeleton equations lots of times, which means we don't worry about balance right off the bat. Now, the reason that we balance is because of this one, the law of conservation of mass. It says that matter can't be created or destroyed. So that means if we have 2 oxygens right here, we have to have 2 oxygens on this side. Like, you can't magically lose an oxygen atom. We'll work in lesson 2 on how to balance it. Right now, we're just concerned with the types of reactions. So this is from your reference table, as you can see down here at the bottom. It's from page 6. You will have this as a part of your NC final exam when you take it. What we need to do is understand what all this stuff is giving us. So for starters, right here it has the 5 types of chemical equations. You have number 1, which is synthesis. 2 is decomposition. 3 is single replacement. 4 is double replacement. And 5 is combustion. There are more than this in terms of types. These are just the 5 basic types that we're going to learn. And it really gives us a really good guide right here with the A-B stuff as to what's happening. And so I'm going to break this down in just a moment. You'll see this again. My point right now is just that you have this in your presence. It can be with you when you take a test. It is not cheating to use your reference table on a test. By all means, I want you to use your reference tables because it should be like your best friend. Let's look at synthesis now in greater depth. A synthesis reaction is where multiple reactants become one product. What the AB thing means simply is that you have one element plus another element makes a compound. So, to give you some examples of those, if you had Na and then maybe B would be Cl2. Together, that will make is NaCl. Now, for people who are going to have trouble with some of these things, a lot of people have issues with why is there a 2 right here and not 1 over here on this particular Cl? Well, because remember, we still have to obey Brinkelhoff. That's why we started repeating this a while ago. Cl is one of the elements of Brinkelhoff. If you have sodium plus chlorine, the way that we're going to write chlorine, since it's part of Brinkelhoff, is as Cl2. Now over here, why did I write it like this? Because we have to throw back to what we used to do. Remember with the charges, like Na has a +1 charge, Cl has a -1 charge. I got those from the periodic table because sodium has 1 valence electron and it's a metal. It will lose it, making it a positive ion. It will be a +1 charge. Chlorine will be a -1 because it's in group 7A. It has 7 valence electrons and it's a nonmetal. And nonmetals, they gain to get to 8. So it'll gain 1 more, making it a -1. Some of you chose to do your formulas this way, where you drew the dots, or just what I'm saying. Sodium has 1, it loses 1. Chlorine has 7, so it gains 1. Remember, the charges are backwards to what they do. So if it loses 1 electron, it +1 charge. And if it pluses 1 electron, it minuses 1 in charge. Then we had to add these up in such a way to make them equal 0. Well, all it takes is 1 of each, so there's my formula. Let's try it with something different just to see how that might work out. What if I had Mg and let's see, like no, I don't want to do that one. Just kidding. We'll put Mg with N. Okay, so Mg and N2. N will still be a 2 because look, it's part of Brinkelhoff. But how do I write what comes over here? Well, Mg is +2 and N's a -3. And if you work it out and do the math of it, it'll take 3 Mg and 2 N's to make this formula correct. So it'd be Mg3N2. I still have 2 elements. I have magnesium and nitrogen. They yield magnesium nitride. Okay. So this is another example of a synthesis reaction. I'm going into over here because I want you to start thinking about formulas. It's probably the #1 thing that students get messed up whenever we do this. Okay. Decomposition. What we're going to do with decomposition is it's just the reverse of these. It'll be one reactant breaking down into multiple things. So we could actually just simply take these and do in reverse. If we had Mg3N2 yield Mg, it is no longer synthesis, it is now a decomposition because we have one thing that broke down. All right, we could do the same thing with the NaCl if we wanted to. I'll give you an example of another one here. So like if we go back to this list right here, let's do a carbonate. So let's do like K2CO3, okay? What K2CO3 would break down into would be K, the metal would go with an O, so that would be K2O plus a CO2. So we'll put CO2. Now, the reason I did this is because this is not exactly one element, it's 2 compounds, but I still see the same basic idea. I have one thing on the left side of the arrow, and I have 2 things on the right. One thing broke down into 2 or more pieces. This still classifies as a decomposition reaction. What I've done is I've put in clues what you should look for to know what it is. So a clue that it's a synthesis is that there's one product. How you know it's one product is there's no plus signs on the right side of the arrow. A decomp is one reactant. And how I know that it's one reactant is that there's no plus signs on the left side of the arrow. Next is single replacement. Okay, and it says the clue is that there's always a single element and a compound on both sides. Excuse me. So for example, if we have A plus LiCl, that would come out to be NaCl. So let's look at my clue. There's a single element on both sides. Na, oops, you know what? I read the wrong thing. That would be Li. Sorry about that. Li. We have Na and Li on both sides. That is a single element. And then also on both sides, I have a compound. There's a compound. There's a compound. So if I see element, compound, then I know that I have a single replacement. And for the record, you can rearrange these either way you want to. I could write it like this. You see what I did? I flipped the thing. It doesn't matter what order they go in. It's kind of like saying 2 plus 5 or 3 plus 2 is 5. It doesn't matter which order you put it in as long as it's true. Okay, so you could flip-flop the 2 ingredients around. Okay, another example of this, and what happened in this is that the Na switch places with the Li. So the Na went in with the Cl and it kicked the Li out. This can also happen with nonmetals. So for example, if we did something like this, if we had LiCl plus F. Now, if you're thinking with me, F, when F is by itself, it should be written as F2. I know that because it's part of Brinkelhoff, and the Brinkelhoffs get written diatomically when they're alone. What would happen in this case is, since the single element is a nonmetal, it's going to spaces with Cl. Li is now going to go with F, and the Cl out by itself. Well, Cl is still part of Brinkelhoff. I'm going to put a 2 on it. Why don't the Li and the Na up here get a 2? Because they're not part of Brinkelhoff. It's just those 7 elements that are part of Brinkelhoff that get a 2 when they're alone. So, here's another example of a single displacement reaction. Now, just for your knowledge, I want you to hear this a lot. There is a bit of a catch with single displacement reactions, and here it is. Okay, so first of all, it says right here, the most reactive metal will be in the compound. So if the element that is single is less reactive, they won't switch places. So how do we determine which one's more reactive? This is also on your reference table. It's on page 7. It's right beside of page 6 with all of that good info that you had about the reactions. Here at the bottom is a table of the reactivity of the metals. So the higher up it goes, the more reactive it is, or more active you could call it. And then down here at the bottom is less active. Okay, so if you go back to this one and you look by itself, and it wanted to switch places with lithium. So sodium is right here. Lithium is, how am I missing it? Lithium is up here at the top. Lithium is actually more reactive than sodium. So what does that mean? That means that lithium wanted to stay with the chlorine. This actually would not happen. So this actually would be, you could write in, like no RXN, no reaction, or no reaction. Actually wouldn't take place. I wrote a lie, okay, because the most reactive compound wants to be in, or the most reactive metal wants to be in the compound. This is the most active or the most reactive. It is not going to give up that spot to sodium. It just won't do anything. Okay, the same thing is true of nonmetals. The most reactive nonmetal will be in the compound. Well, here's your little table of nonmetals. It's very small. Fluorine is at the top and iodine is at the bottom. This one dealt with the switching of fluorine and chlorine. Well, fluorine's higher than chlorine, so this one's true. This one is a true statement. I made this one happen for real. Like fluorine would give chlorine the boot and take its place over here with lithium and kick chlorine out by itself. This one would actually happen. This one would be a big like no. Okay. You don't have to know that necessarily at this point. I am getting a little bit ahead of myself, but I do want you to kind of start thinking about what's happening because it's coming up. Okay, double displacement and combustion. These are easier. There's no strings attached to these. A double displacement or double replacement is where you have 2 compounds on both sides. So here's the generic form right here. Oops, I drew a line through it. For example, if we had NaCl plus MgO, okay, what this would make is Na2O and MgCl2. I would be able to identify this right here as a double displacement because I see compound, 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 and compound. There's no single elements. It doesn't make one thing on the right. I see a plus sign. It doesn't have one thing on the left. I see a plus sign. So this is a double displacement or a double replacement. There's 2 words. You could use either one you want to. Okay, I'll have both in the answer choices for the test. Okay, the last one is combustion. And the clue here is that there's always a hydrocarbon. You always have something with C's and H's. It may have O's in it as well. But then the rest of it, all of this is identical for every single reaction. So you'll have O2 yields CO2 plus H2O for everything else. Like the only thing that changes is what comes first with the CH's. Okay, so what I'm going to do is I'm going to skip ahead here. through some of these, and we're going to look at these to see if we could identify the type of reactions that they are. So what is this? Well, here's what I notice. I see a compound and a compound, another compound and another compound. How I know they're compounds is that they have a capital letter and a capital letter. There's 2 capital letters per group, then this is a compound, 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 compound. When I see 2 compounds on each side, that makes this one be a double replacement because it's not making one thing over here. It doesn't start out with one ingredient. There's no CHs and O2s, nothing like that. I don't have any single elements. It's got to be a double. What about this one? This right here, that's an element. I know it's an element because it's 1 capital letter, like that's the element for zinc. This is a compound. This is an element. I'm sorry, this is a compound. This is an element. Even though there's 2 of them, this is just H. It's 1 capital letter. So if I have element, compound, compound, element, then this would be a single replacement because it's got the single thing. And what I see happening is the zinc is trading places right here with the H. They swap out, so it is a single replacement. On this one, the Si is going with the F. So the Si and the H are switching out. And you could also think of it as the O and the H are switching, or the O and the F are switching out. So it's a double switch. This is just a single switch. What about this one? This is a compound. I don't see any plus signs over here. Like there's plus nothing else. It's just this one thing. I don't even need to think beyond this. When I see 1 starting ingredient, then I know automatically it's a decomposition reaction because it starts out with 1 thing and it breaks down into 2 pieces. What about this one? This is a compound. I see lots of capital letters. I see a plus sign and another compound. I have compound, compound, and then it makes another compound and another compound. So that's going to make this one a double. What about this one? Same thing. Compound, 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 compound. It's going to be another replacement. What about this one? Element, element, compound, and compound. And actually, this is missing something here. Like this is not written anywhere near correctly. I think I'll have to go back and look at it. Like it's missing the H's from this side. So like this whole thing, we're just going to put needs work. It doesn't match up with anything because I don't have this right at this point. I'm not ready for this lesson. Actually, looks kind of like this one. Right here, what do I have? I have a compound. I have an element. I have another compound, and I have another compound. So now, okay, stop and think for just a second. I didn't have anything that matched up with this. This half right here looks single because it's got a compound and an element. But this side over here looks like a double replacement because it has 2 compounds. You don't have anything that is mixed. So what you could put on your worksheets when you get to this is just NA. It's not applicable because not everything applies to exactly what we're doing. We're working on the 5 types. So if it doesn't match the 5 types, it doesn't apply. So you can put NA for not applicable. What about this one? Well, here's what I see. I see CHs, and then over here, this is the end of our recipe for a combustion reaction. Oxygen making CO2 plus H2O. So this is a combustion. And what a lot of my students do is they want to look at this and they want to go, okay, well, this is a compound right here. And there's an element. It's a single replacement. They just look at 1/2 of it and they fail to look at the whole picture. So please look at everything. What's this one? Well, look, it's almost exactly like this one. I see CHs, and then I see the recipe of a combustion. So this is a combustion reaction. Oh, look, again, I see CHs and the rest of the recipe for a reaction. So yet again, I a question reaction, okay? So this is what you're going to do now. You are going to do practice time. What you have is you have a sheet that actually has a place for you to balance. We are not doing that right now. You are only to do the column on the right where it just has a bunch of blanks where you need to go through and do what I just did with these. You need to go through and identify the type of reaction, and if it's none of the ones that we just did, put NA. Okay, if you need to see me work some of these so that we could figure them out together, then please let me know if you're going to join me for office hours or if I need to come up with an office hours just for you.